All right, so today we are going to do more math. So we're going to talk about, and unions of infinite collections of sets. So this is something else that we need to compute things. Bound property of the real numbers. Okay, so it's kind of a wordy title here. So I wanted to just talk about intersections and unions of sets, but in the last class, I ended up talking a lot about this. So then I just got to throw this into the title. Okay, so so often we're going to consider families of sets. So we are often interested in families of sets. So these are sets of sets, families of sets, indexed by another set. Okay, so so let me just show you some notation for this. So the notation. So we sometimes consider these as like this: AI for I, an element of I. These are two different notations for the same thing. AI, I, and I. So this I here, this particular I, so this is the index set. And these guys here are, these are the sets. These are sets, and this is one for each I and I. Okay, so we're going to form sets of sets. So this is what a collection of sets is. Okay, so let me give you an example. So let's start with the 0th example. Okay, so we can consider if I is the set 1, 2, up to n, then it's a collection I and I. So this is the same thing as a set A1, A2, AN, where each of these guys AI is some set. So we could make something concrete, like I don't know. We could say something like AI is the set I plus 1 for concreteness. Okay, so here's one example of a collection of sets. So here we have one. So this is actually, let me do a vertical bar today, so not to confuse the eyes. Okay, so I'll use this symbol today. Okay, so here this is just a collection of sets. So it's a set of sets, one for each n. Okay, let me give you another example. So here we could have I. This is going to be a totally, well, let's do BI. Okay, so this could be I plus, let's do 0. Let's do this interval here, 0 to 1 over I for I in, let's say, the natural numbers. So this is our index set here. This is the index set, this particular collection of natural numbers. And these are our sets like so. Okay, so let me do a drawing here. Okay, so here's 1. So B1 is this whole thing. Okay, and then if this is a half here, right, B2 would be this thing, would be this interval. And then if we do a third, hopefully this is a third here. So this is like B3 and so on. So they're a nested collection. And then B4, this is supposed to be a fourth. So B4 and so on and so forth. So here we have a bunch of sets, right? I guess I don't need to really include this part since it's just a subset of the real line. This is a subset of the real line. Okay? So we have this sequence of sets like this. Okay? So they're indexed by this collection here. So I just want you guys to recall for a second. So just for A, B real numbers with A less than B, by this A, B, I just mean the set of X such that X is in between A and B. Okay, so that's what I mean, right? So so this is just this interval like so. Okay, does that make sense? Yeah.
Say AI equals the set.
Yeah, I was just like giving you so like I wanted to do an example. Okay.
I just don't know what it says inside.
Oh, AI this is I and I plus 1. So you can make this set to be whatever you want, but I wanted to give an example, but I wanted to be concrete, so I wanted to specify the sets. But in this example, I just wanted to show you that when you have this set here and it's just the numbers 1 through n, this is the same thing as giving a collection, a finite collection where you have n elements here. That makes sense? Okay, and I did I and I plus 1. I'll use this set again. Okay, so so here, let's do another example. So 2. So we could consider Bn, or let's see, we already did B. So let's do Cn. So this could be the set of n plus 1 for n an element of the natural numbers. And so this could be J. So this is an index set. Or index. Okay, and so these are just the collections of 2 elements for each of these. So let me draw a picture here. Okay, so here is 1, 2, 3, 4, 5, 6, 7. So, okay, so this thing here, this collection is C1, these 2 elements. This is C2. This collection here is C3. This collection here is C4. This collection here is C5. And this collection here is C6, C6, and then you could keep going. Okay? So we have another infinite family of sets. Okay? These happen to be subsets of the natural numbers. You can view them as subsets of the real numbers. It doesn't really matter. But it's just like for each index here, I'm going to get a different set. Okay. All right. So we have index set J. Okay, so the index sets don't need to be I. They don't need to be J. You know, so you can have them be whatever. 1, 2, 3. So here's another example. So D alpha could be the set of. Let's do an interval thing. Alpha squared, and then alpha squared plus 1. Okay, for alpha an element to the real numbers, here we'll call this set K. Okay, so this is our index set. Okay, so here, now this is an infinite collection. Now this is like a continuous collection of sets. And so you can see here these were kind of like discrete, right? But now, let me try and draw this. So for a given alpha, you could have like alpha squared here, and then alpha squared plus 1. But as you vary alpha, right, this whole set, this is d alpha. As you vary alpha, this thing will vary continuously. You see what I'm saying? So you have a whole thing. So this thing varies continuously. Okay, so we have a set of sets, right? And notice that here, there's even repetition here. So d of alpha is the same thing as d of minus beta, and that's okay. Okay, so you can have repetition. It doesn't really matter. The overall set of sets is the same without repetition, but if you want, you can consider, you can specify the same set. So note. D of beta is equal to d of minus beta. This collection of d beta for beta in the real numbers is equal to the collection of d beta. Oh, let me do this. We were doing these today, huh? D beta for beta in the non-negative real numbers. Okay, so these are the same, right? But you can still specify them with repetition if you want. It doesn't really matter. Okay? Okay. Okay. So given such a set of sets, so these are the end of the examples. Here, all the way. Okay. So given a family of sets, this is just a set of sets. Here, AI, I in I, we can define the infinite intersection, in union of all the elements of all in the family. So by all the elements of the family, I mean all the sets. So here, so we can define, say, the intersection for I and I of AI. Okay, so how should we define this? So this is the set of X such that something happens. And what should that be? So we have a big intersection.
X is an element of A1 union, or intersect A2, intersect A3.
Yeah, so on and so forth. But now we have it's not clear that, so we can't write 1, 2, 3, 4. But that's the right idea, right? So we use a big conjunction, and the big conjunction was the same thing as a for all quantifier. For all I and I, X is an element of AI. Right? So this is saying that it's an element of every single AI. Okay? That's how we define it. So this is the definition. Okay? A sub I. And it's defined to be equal to that. So I is equal to I here. And so what should this one be? This one is like a union. And so if it's true that X is in a single one of the AIs, then it should be in this union. So that means that there exists some I such that X is an element of AI. All right. So these are the intersection. This is how we define intersection and union. All right. So let's do some quick examples. So what I want to do, and this is why I'm going to have to talk about the least upper bound property, but let's do, let's say this one. So this is without proof. Proof for now, just so we can understand the meaning. So the intersection here of, for n in the natural numbers of this set n, n plus 1, what should this be? So here, let me make this drawing for you guys again. So here's 1, 2, 3, 4, 5, and we had things like this. So what's the intersection of all those sets? Nothing. So this is the empty set. Okay? And let's do another one. So what's the union of all these sets? N plus 1. Yeah, n plus 1. What does this one look like? Yeah, this is all the natural numbers. Okay? So this is the union of all those sets here. So this is, you can see this one as well. Okay, so I want to be able to prove, so what I want to do is I want to be able to prove these things. Okay, and in particular, I want to prove, let me do another example. So one more example. Okay, so let's do the intersection for n in the natural numbers of the interval 0 to 1 over n here. So what should this be? So here, let me draw the drawing for you guys again. So here's 1. So we have this one, and then there's a half. So we had this one, and then we had a third. Then we had a fourth, and then we had a fifth. 1/5, and this is the point 0 here. Okay, so what should the intersection of all these things be? Yeah, so this should be the empty set as well, right? So this should be.
Why would it be empty if they all contain 0?
They all don't contain 0. The 0 is excluded because this is an open interval. Okay, so. And that's a good way to check, right? So if you did have a closed interval here, then it would contain a closed endpoint there is not an element of 0a. Let's say greater than 0. Okay? So yeah, these will all be excluded here. So this is the empty set. But what's kind of sneaky is to prove this one, I actually need to tell you guys a little bit more about the real numbers than we've been using up to now. Okay? So but now I'm going to do like a little break. Okay, from this stuff, and I'm going to tell you about the real numbers a little bit, and then we'll come back and we'll be able to prove that thing. Okay, so right now we actually can't prove it. Okay, so let me. Here we go. Okay, so I want to talk about the least upper bound property. Of the real numbers. Okay, so we haven't really talked about what the real numbers really are. And I'm not going to tell you what the real numbers are today, but let me just say that they're a very complicated construction. Okay, so let me just say a little bit about the history of the real numbers. So the concept of the real number, I think, it goes even back to Archimedes, where Archimedes recognized that the decimal expansion of pi, right, goes on forever. So he was the first one to really give an inequality for pi, right? And so he recognized that if you take a number that you could infinitely expand it. He didn't have the decimal system. He didn't have that yet. But I think people recognize that there was a possibility for numbers to have infinite decimal expansions early on, or what is the mathematical equivalent of a decimal expansion. Okay. And people were using numbers like pi and e and stuff like in the 1700s early on, right? And it wasn't until the late 1800s where Dedekind and Cantor, the same Dedekind who was worrying about the axioms of the natural numbers, right? They actually gave the definition of the real numbers, okay? And so one of the key properties of the real numbers is the following thing, okay? So this is one of the things that they figured out. So the least upper bound property. And what it'll do is this property actually excludes infinitesimals from existing in the real numbers. Okay, and it says that, so for every subset of the real numbers with an upper bound, so let me say every subset, let me just do it like this. Every subset with an upper bound admits a least upper bound. Okay, so let me explain what these things are. So let me give you a definition. So an upper bound for a subset of the real numbers is a number, is some m in the real numbers such that for all x in this set, we have that x is less than or equal to m. That's an upper bound. Okay? So this is an upper bound like so. So let me give you an example. So if a set has an upper bound, so if a set has an upper bound, we say it's bounded from above. Okay. So let me give you some examples. Okay? So if S is equal to the real numbers, this has no upper bound. Okay, so here, we have the whole thing, and there's no largest number. There's no number bigger than all the other numbers. All the others. Okay? But if S is equal to the set, say, A, B here, then let's say, let's do this. Let's make this more concrete. 1, 2, then m is equal to 3 is an upper bound. Okay? Also note that, so this number L is equal to, it'll turn out that L is equal to 2 is the least upper bound. Okay, so does this make sense what a bounded set is? So here, let me give you another example. So are the integers bounded from above? The integers are not bounded from above. So here's another example. If S is equal to Z, has no upper bound. The negative integers has an upper bound. The upper bound would be 0. Okay? Okay. So, all right. So this is another example with no upper bound. All right. So at least, let me give you a definition. So a least upper bound for S is a number L such that for all L prime less than L, there exists some y in S such that L prime is less than y. Okay, so this is what a least upper bound is. So it's like so anytime you go lower than the least upper bound, it's not going to be an upper bound anymore. There's going to be something that violates it. Okay, that makes sense. So like here, so the idea here. Okay, so the idea is that once you go lower, than the least upper bound, you will find, elements larger than that. Okay, so some remarks are in order. So first of all, here, so L is 2. So note that L, the least upper bound is not an element of this set. Okay, so note, so the least upper bound, let me do this, least upper bound is not necessarily let's say least upper bound of S is not necessarily an element of S. Okay, so for here, S is equal to this interval AB, right? So L is equal to B, but L is not an element of AB. Okay, so B is not an element of here. Although if I were to go slightly smaller than L, right, then you can always find something that's in this interval. Does that make sense? Okay, so here in this example here, so once you go smaller than B, right, you're going to find something in here that's bigger than that number. So if I go to like B minus a little bit, right, I'm going to find something that's in here. And notice that this element here is not necessarily achieved by this. Yeah?
So you can't reach B, but if you take a small piece off of B, you'll find something in between A and B?
Yeah, if I take a small piece off of B, if I take a small piece off of this least upper bound, right, then you're going to find something in there that violates it. Otherwise, that would be the new upper bound, right? And that would make it so that this one's not the least one. Okay, so that's why it has to be the least one. So this is kind of a weird. So the thing about this is that you're never going to be able to you're not always going to be able to know what the least upper bound is. Okay, so the idea is that you could have some crazy set. Okay, so here's kind of a picture. Here's the real numbers, and then you could have something like crazy going on. Okay, and so like maybe you don't know how to describe it, but you know that if you're given some m, you'll be able to find the L here that's the least upper bound. And here's the drawing of S. So this could be crazy. And so the idea is that knowing an upper bound, it's not that every set has a least upper bound. An upper bound M gives you a least upper bound. Okay, and that's what the condition says. It says once you have this one, this upper bound, you get a least upper bound. All right. So once there exists one, there's a least one. Let me also say something else. So another terminology. So the least upper bound is sometimes called the infimum or the supremum. Called the supremum. Okay, so that's what a least upper bound is. Okay. All right, so great. So now using this least upper bound property, I want to do something with this. Okay. So, so there's this thing called the Archimedean property. So there's a lemma. Okay, in Archimedes, so I think he was like 100 BC, right? Maybe later. I get him and Euclid mixed up. No. Okay. So I think he's around 100 BC. Right? I might have to correct that. But he was so smart that he realized that these properties about the real numbers that I gave you, that least upper bound property, that you couldn't prove, at least with his technology. Right? And so he recognized this, and this is one of the properties that he stated. And we can prove this now, right? But for him, it was an axiom. Okay? And for him, it said for all x, which is a non-negative real number, there exists a natural number such that 1 over n is less than x. Okay, so he recognize that. So this is an obvious thing to us, right? Is that if you take a large enough integer, right, you can make it smaller. 1 over n will be smaller than a number. So it's like, you hand me a small number. Well, I can always find a 1 over n that's smaller than that. Okay? That's kind of, it seems silly, right, that we'd have to prove something like this, but we do. Okay? So let's do less than or equal to here. All right. You can do less than too. It'll be the same. So if I have this one, if I just did n, if one of these exists and I did n plus 1, right, that would give me one smaller too. So it's the same thing if ever we're going to do less than or equal to or less than. Yeah?
So it's sort of improvement that you want to examine one, or like finding like another, doesn't exist a smallest real number?
Well, so for showing that there's no smallest real number, you could just take a real number and divide it by 2, right? This one's more complicated, right, in that here I'm showing that there exists an integer such that 1 over n is less than x. Okay? So that's what I'm doing. And the reason I want to use this is I need this property in order to show that that intersection of all those intervals is 0. Okay? This is the thing that I need I need that for. Okay. So let's do the proof. Okay? So here's the proof. Okay? So let's suppose not. Okay? And so we will consider the set S, which is the set here of y in the real numbers, in the non-negative real numbers, or let's say positive real numbers, such that y is less than 1 over n for all natural numbers like this. So this is something like, suppose we have an infinitely small thing, a non-empty set. Okay? So this set is bounded above by m equals 1. Okay? So by the least upper bound property, it'll have a least upper bound. So since this set is bounded, it has some least upper bound L. Okay. So let's do this. So let me make the drawing. Let me just show you a drawing here. So here's 0. And then S is something here. And we know that 1 is over here. And since there's this bound 1, right, we get to conclude that there's a least upper bound L. All right. So what I want to do is I want to violate this. So I want to show that I want to produce another. What do I want to do? I want to produce an upper bound. Okay. So we have this least upper bound here, and so what I want to do is I want to produce a contradiction. Okay. Okay. So since 2L, okay, so this is bigger than L, right? We know, here's 2L, and here's our set S. We know 2L is not an element of S. Okay? So what's the definition of S? Right? The definition of S says that this thing is so we know, so i.e. not this statement. So let me do it like this. Not for all n in the natural numbers, y is less than 1 over n. Or let's say 2L. Okay, and this is saying the same thing as there exists some n in the natural numbers such that 2L is greater than or equal to 1 over n. All right. So let, since there exists one, be such that 2L is greater than or equal to 1 over n. Okay, so this implies that L is greater than or equal to 1 over 2n. Okay. So now we have something like here, this is greater than or equal to 1 over 2n. Okay, so this means, so we take some y, so we can take some y that is slightly less than L, and produce here, so that y is so 1 over 2, say n plus 1, like this. Okay, and so this violates, so here, and so here this is so 1 over 2 n plus 1. This thing here is strictly bigger than L, right? And there, since this is this is strictly less than L. Okay. And there exists a lower bound, but let's say bound of the form 1 over n. So does this make sense? So let me kind of describe what's going on here just again a little bit. Let me just repeat this to hammer this in. Okay, so here we had this upper bound of 1 over 2n like this. Okay, so we said by the least upper bound property, right, if L prime is equal to 1 over 2n plus 1. Okay, so this thing we know is less than L. Okay, in particular, because this is because we have this thing, 1 over 2n plus 1 is less than or equal to, or is strictly less than 1 over 2n. Okay, this is strictly smaller than this. I'm dividing by something larger, so it's smaller. Okay, so we have this thing is less than this. And so since it's a least upper bound, by the definition of least upper bound, right, there must exist, it's no longer, this is no longer a bound, right? This is no longer an upper bound, meaning that there exists some element in here that is bigger than this one. Some y, an element of S, y is greater than or greater than L prime. Okay, by the definition of this. Okay, but this is a contradiction, right? The contradiction comes from the fact that. So what's the definition of y? Right? Y is supposed to have the property. So y has both the property here, both the properties here, well, that for all n in the natural numbers, y is less than 1 over n, right? And it also has the property that y is greater than L prime, which this thing was 1 over 2n. Okay, and this is a contradiction, right? This is a contradiction. Okay, does that make sense, guys? So like, what we did is we produced, we produced something that's supposed to have this and this from the least upper bound property, which is kind of sneaky. All right. So, so when do we end here? 11:40. Okay. So let me just say how we're going to use this, and then and we'll do some more exercises. So we're a little ahead of the other class again. Okay? Okay, so we are going to use this next time. We will use this to show the intersection of this thing 0 to 1 over n in the natural numbers is empty. Okay? Okay, so well, maybe I can just do the proof really quickly for this particular one. So let me show you now I can prove this. Let me just prove it. Okay, so the proof. Okay, so suppose x is an element of this set here. Here, from 0 to 1 over n for n in the natural numbers. Okay, so then I'm going to show that this is false. Okay, so I'm going to show that this is a contradiction, and that's the same thing as showing it's an empty set. Okay, so we will show. Okay, this means for all n in the natural numbers, x is an element of 0 to 1 over n. Okay, so this means for all n in the natural numbers, x is less than 1 over n, right? But this is a contradiction, right? This directly contradicts the Archimedean property. Okay, so we actually have this. Okay, so we have a positive number, and it's less than 1 over n for all n, and that's just false, because we proved that for every positive number, there exists something, a 1 over n, that gets you smaller. Okay, so this shows that this statement here is false. Right, so, okay. Is there any questions on this? Okay.